But dynamics and chaos, we still have so much cool stuff. All right, so anyway, this topic is like the coolest thing. You can just, whatever, you can and should take other classes, read books about this. There's so much cool stuff. But we are gonna tidy ourselves up today and just mention how it touches on chaos and what chaos is about through one particular lens, but I think that gives you an opening into a wider world of ideas. So last time we were talking about solving a simple two-dimensional equation, and we talked about it, the ideal model we had in mind was something that has a fixed point in the middle and two different dimensions, and we studied a system that was like a matrix system like this, and then we had A, B, C, D, like this, X, Y. So this is a simple, linear, homogeneous system. Or you could think of it as being near, the fixed point didn't have to be at the origin. It could have been anywhere. We could have Taylor expanded nearby to get this. But I just wanted to finish off this topic because there's actually a cool, we can explain all of the possible solutions to this problem in one simple figure. Well, sort of, it's not simple, but one very complicated figure. But anyway, it gives us the idea of a regime diagram, which is an important concept for thinking about this kind of stuff. And so it's just one nice example. So I wanted to finish on that before we jump on to one related concept, basins of attraction. Okay, so last time we had kind of we had two eigendirections that were kind of like this, and they were coming in and going out, and we talked about how this would be like, depending on which direction you were going, there was flow going by. Remember that closing idea? So we saw how there were two eigenvalues of the diagonalization of this system. Those two eigenvalues told us if they were negative, that we were coming in along that direction. If they were positive, we were going out along that direction. So that was pretty clear. And then if you're nearby, you're kind of a little of both, right? You're just flowing along. Everybody on board with that? We could, and remember we wrote this as a kind of matrix equation, and then we talked about the properties of this matrix. That was how we found the eigenvectors of the matrix, and we on the eigenvalues of the matrix, and that was what helped us to find out where these things were located. And it wasn't quite this matrix. It was a slightly different one that we said had to be not invertible to get the solution to work out. Okay, but we could do something. So one interesting thing about the eigenvectors and eigenvalues is that the trace of this matrix, so this one plus this one, and the determinant of this matrix, this one times this one minus this one times this one, are unaffected by what coordinate system we're in. So the fact that we went into the eigenvector directions, with the eigenvalues representing the matrix, doesn't change the trace or the determinant. Okay? So if I went into that other coordinate system and said now, if I twisted and stretched everything the way that we said that was one way to think about what eigenvalues mean, I could still look at those two objects and they'd be the same. Does that make sense to everybody? Sure. Okay, so let's just write down what they are. So I have in the notes, I have the trace is A plus B, and the determinant is AG minus BC. And so if both of the eigenvalues are negative, what's the trace going to be? It's going to be negative because the sum of the diagonals, these are not the eigenvalues, but we know that this would have to be the same as the sum of the eigenvalues, because in the diagonal matrix version, this would be the same thing. So if these two were negative, then these two would be negative. Does that make sense? If the determinant was negative, or the determinant was 0, or there were relationships between the determinant and the trace, it would be preserved. Does that make sense to everybody? Okay, so here's the regime diagram then. So if you map in a space where we have the determinant and we have the trace, and we draw a quadratic like this, where this is sitting on trace squared equals, trace squared minus 4, determinant equals 0. This is everything. Unstable spirals, stable spirals, stable nodes, saddle points. It's all over here, saddle points. So both sides. Up here is unstable nodes. And then these on this line are called stars or degenerate modes. And fixed points are sitting on that line. Okay. So let's think, all right, if both of the eigenvalues are negative, we're on this side of the diagram, down here below. So notice everything is stable, stable, stable. Saddle points are part stable, but things are converging in on that side of the diagram. Above, unstable, unstable. Things are diverging out. They might be diverging out like this, kind of in all directions. Or they might be diverging out much faster in one direction rather than the other direction. Does that make sense to everybody? So in this case, the two eigenvalues are unequal. In the first one, they were kind of equal. But it could also be spiraling outwards if the eigenvalues had an imaginary component. Does that make sense? Or spiraling inwards. This little diagram, here are the spirals that are stable. Here are the spirals that are unstable. Here are the nodes, which is like this, just going out without the imaginary part. So can anybody see easily why this funny function has something to do with the imaginary bit? Any guesses? It's a little hard. It's a subtle point of what we did yesterday. Remember we came up with an equation that was like m squared, plus, a times m plus c equals 0 for that. This was the thing in the exponent. We had something along those lines. So what has to happen here to get spiraling or circling motion?
Solution needs to be imaginary.
Solution needs to be imaginary. So we could study this and find that n equals minus a plus or minus square root of blah, blah, blah. So that thing inside the plus or minus square root has to be negative. And it turns out this is the condition for it to be negative for an arbitrary matrix. You can actually write it just using these two guys, right? And you can see that these have the coefficients that are going to come into that. So without doing the algebra, you can imagine how that goes. So imaginary eigenvalues in here, real eigenvalues out there, that kind of thing. So why is this a useful thing to do? To make this regime diagram. And how generic would it be? What's helpful about this?
This applies to any coupled homogeneous ordinary differential equations.
Yeah. And in fact, if you're thinking about Taylor series near a fixed point, near a steady state solution, it actually applies to all of them because we already know how to add in the steady state piece on both sides. We still get something of this form. So whenever you're near a steady state where x dot and y dot equals 0, you can use this diagram to explain it. You have to, correct this and write down this matrix where these are the components of the Taylor series, but we have all the tools to do that in general. So every time we have a fixed point, we can use this diagram to explain what the possible behaviors are of 2D convergence n. We can fall in, we can fall out, we can go in one direction and out the other, we can spiral, we can just oscillate around and around. That's it. Those are all the possibilities. But to get to a limited set of possibilities, we had to Taylor series and linearize, so we had to truncate with the linear order. So the last thing I want to leave us with is what happens farther away from the fixed point. So now, though there's a lot of complexity to this does actually just like we had the one-dimensional ODE, we can just write down the answer. So this is kind of the same thing. This is a qualitative descriptor of the total 2D ODE. We can understand all the possible behaviors just by going through this procedure, but only in the local linear limit. Now I want to think a little bit about what happens if we had a nonlinear system. So I have a toy nonlinear system, which I'll leave that up for now. Which looks like this. Oh wait, that's not the right one. I'll write down the simple one. D by dt. X minus of x dot of x and y equals. Okay, now we're getting fancy. E minus x minus 2 squared minus y plus 1 squared plus e to the minus x plus 1 squared minus y minus 2 squared, y minus 2 squared. Okay. All right. So what's going on in this crazy equation? So what are these things? What kind of shape are just the thing inside the parentheses? Square brackets.
Circle.
They're circles that are centered around, they're like Gaussian humps. And there are two of them and they're added together. There's one that's located at x equals minus 1, y equals 2. And there's one that's located at x equals 2, y equals minus 1. So let's draw that on a map. X. So there's a hump of unit magnitude at x equals 2, x equals 2, y equals minus 1. So if I draw some circles, some contours like that, that's this field, and so it's high here and then lower elsewhere, across the middle. And then that's added together with another one that's centered at x equals minus 1, y equals 2, like this. And then in between, they're going to kind of add together. Okay, so that's the thing inside the gradient. So what's the gradient of this? This is like two hills. What's my gradient field like? Right, it's going to point uphill. It's kind of everywhere. Right? That's what we know about the gradient. So this is like a potential function or a height field, and we're thinking about the direction of maximum increase of that height. Everybody on board with that? And now we just say rate change of x and y is to go towards the high spot. So wherever we are, we're going uphill. That's what this differential equation says, and we have these two hills. Okay? Everybody on board with that? All right. So are there fixed points in this system? Yeah, there are. Where would we go, and then we'd stop moving? If I get to a peak, I'm stuck there. Everywhere I go, it'll be downhill. So that is going to be a stable fixed point here and a stable fixed point here. Cool. Are there any other fixed points in the system? Between them, on the spot between them. So that one's a little harder to find. How can we find this one? So this is an important concept of something called the null climb, which remember when we had the 1D phase pictures, we'd drop our fixed points and then we'd say, oh, whatever. Suppose our graph is going like this. We would say when we're above, we're headed this way. This is x dot, and this is x. When we're below, we're headed this way. When we're below, headed this way. And so this was unstable, this was stable, that little game we played. When we got to this point, what do we know about x dot at that intersection? X dot equals 0 at the fixed point. Over here, we could set either x dot to 0 or y dot to 0 or both. To get a fixed point, both are equal to 0, right? But what if we just set one of them equal to 0? What would that tell us about the solution? So I have actually plotted these on top of this figure, which looks something like this, and something like this. This one is y dot equals 0, and this one is x dot equals 0. And all I did to do that was just plug in on the right-hand side, take the gradient, and then the x derivative is going to be equal to the x component here, and the y derivative is going to be equal to the y component here. And then I just plot the function that comes out by setting x dot or y dot to be 0. Everybody see how that goes? Okay, so how do I interpret this x dot equals 0? What does it mean that x dot equals 0? Does it mean that I'm not moving when I'm on this line? It just means that part of the motion is not allowed. Which part? The motion in the x direction. So I don't know whether the arrows go up or down, but I do know that they're all along the y direction only when I'm on that line. Okay, so look and see now. There is definitely an incoming here, upgoing there, and then on this one it's not so obvious, but apparently if I drew the little arrows on here, they would have to be just vertical. I'm guessing that they're going towards that one there, and then probably towards that one there. Everybody see what I mean? And then it's going this way here, and it's going this way here. So those all have x dot equals 0, but y dot is whatever it is. What about on the y dot equals 0? Same thing, except now I can move this direction, but not that direction. So I'd have an arrow here, I'd have an arrow here, and I have arrows, horizontal arrows here, and then they flip and go that way towards the other. Fixed point there, fixed point, fixed point. All right. So does everybody get how that works? So if I'm on this line, I'm going to move along that line. If I, straight in this direction, but I'd move off the line if I were here. So it doesn't block my trajectories exactly, but it helps me map them by knowing where they're parallel to one axis or the other. Okay, so if I'm out here, where do I go? What do you think? Probably towards this one. If I'm over here, where am I going to go? Down towards this one. If I'm right here, where am I going to go? Kind of down, maybe this way first, or maybe this way first, but I'm going to head towards that one. So there is the notion that I might have regions of the domain where I'm going to end up in this fixed point, regions of the domain where I might end up in this fixed point, and they're kind of dividing up the space. That concept is called a basin of attraction. There's a basin attracting to each mode. Okay, and for this solution, I think we all agree that there's like a line in between, and pretty much all the ones on that side of the line end up here, and pretty much all the ones on that side of the line end up there. So this is a problem where we can find the basin of attraction pretty easily. Does that make sense to everybody? Yeah.
So was it where x star is equal to 0 and y dot equals 0, where those lines intersect? Is this yours? Points, or was it where they are intersect 0?
Good question. What does this equation tell us? DDT, both x dot and y dot equals 0 occurs where? Everywhere on this point, everywhere on this line, x dot is equal to 0, and everywhere on this line, y dot is equal to 0. So where do both x dot and y dot equal 0? At the intersection. So the unstable fixed point sits at this intersection, the stable one sits here, the stable one sits here. So all the fixed points will always be on the intersecting sections of the null clines. That's a reason why the null clines are useful, but the null clines are also useful because they're helping you map the flow field. Yeah?
If we were just given the x dot and y dot curves, and we were expected to tell, would we be able to tell you whether the fixed points are stable or unstable? Because would we be able to draw the arrows on which one?
You can draw the arrows. It might be super complicated. It might be really nasty. It might be going in one direction and coming out in one direction. So what could you do? You could take the Taylor series near the fixed point that you just found by looking at the intersection of the two null clines. Take the Taylor series, use this diagram to tell you whether it's stable, unstable, the spiral, the star. That's the game we just discussed. The null clines help you find the fixed points. If this was a horrible function, in this case we actually can just write down what the intersecting points are. This one is going to be halfway between those two, and this one is the peak of each of those points, right? We can actually do that pretty easily in our head. For a really complicated flow map, we might actually have to numerically plot the null clines and zoom in on the intersection to get an approximation to them, and then numerically Taylor series nearby. But we know how to do that. We just have to follow the steps. Okay? And in this set of problems, this dividing line between is kind of like the continental divide. Like all my flow patterns on this side go to this peak. All my flow patterns on this side go to this peak. It's a little funny, I could have put a minus sign here. That probably would have made more sense to make these holes rather than peaks, but whatever. That's okay. Does everybody understand what I mean by the continental divide? There's like that continental divide is a separatrix between the basins of attraction. Okay? So it separates two different basins. Okay, so there's one more type of nonlinear system I want to talk to before we talk a little bit about, two more types of nonlinear systems, and then I want to show you some pictures of separate basins of attraction that would be kind of interesting. Okay, so we talked about the logistic growth map, which was the one that was like this, and a stable fixed point here and an unstable one there. And before we called this number, right? So our flow, so this is, this is, we were calling that number, but let's call it R instead of N. We called it N before. So if R dot is greater than 0 on this, and so I have a function that looks like this, everywhere I'm going towards this, and so this guy is a stable one. But I want to add another equation to that system, which just makes it really fun. Where R dot equals R times 1 I'm inviting you to imagine spinning this thing around in theta and having it be a polar coordinate system. So I'm rotating around this axis at a constant rate, but I still have this kind of dynamics where I have a stable fixed point here and an unstable one at the origin. Everybody on board with it? So we agree these equations sort of correspond. What does this map, this phase plane map, look like for this system? So if I wanted to draw a phase portrait of that, but I really wanted to draw, let's draw the polar coordinates to make our life easy. So r is distance from the origin, and theta is going round and round this way. So what does it do if I start it out here? So we go out from the origin, which is an unstable point, and it's going to eventually get onto this circle. It's the stable point over there, and r equals 1. That's where this is that. Everybody. So this is a stable thing, and the trajectories inside are all going to spiral outward toward it, and then converge into it. So everybody see how that works? So we're spinning around and around this axis, where we have a stable fixed point if we weren't spinning, but now we are spinning, so it becomes a stable loop, a limit cycle, it's called.
I guess I'm not really conceptualizing this. I understand like the limit is the circle, but I'm a bit confused with how you know it travels like a bit up and then around.
Right, so I'm looking for, this is the axis, this is this axis. I'm now imagining it spinning this way out of the board, and I'm just looking from above. And so in time, we know that we would go this way in the r direction, but in the theta direction, we're just spinning around in the other way. So whatever I start, I'm going to be spinning around with theta direction. But if I start right on this point, it's an unstable point, but if I start right off of it, I'm going out, and I'm eventually going to get to r equals 1. If I start out here, I'm also going to zoom in and eventually go to r equals 1. Because if I started over here, r dot would give me that way. Does that make sense? So this is sort of like, remember our phase portrait for the imaginary eigenvalues in the linear system, because we're just going round and round, but it's different in one really important way. What is one of the characteristics of a linear system? Remember the big boulder? You push on it a little and it doesn't fall, you push on it a lot, it does fall. We said that was a characteristic of nonlinearity. It depends on the amplitude. In our inertial oscillation, pull it down and let it bounce, that guy, the bouncing water or air parcel. It didn't matter how far we pulled it, it still bounced. And it bounced with the same frequency no matter what. What about this system? Does it always have the same amplitude as it goes around and around? If I pull it down a certain distance r, say 2, and let it go, does it oscillate at r equals 2? It doesn't. So it's not like the linear oscillator. It collapses down to r equals 1. If I pull it out to r equals 1/2 and let it go, it expands out to r equals 1. So this is an oscillator. Goes around and around periodically. We actually know the period. The period is just 1. But it's a nonlinear oscillator. It's a limit cycle. It is not independent of the amplitude of the oscillation. It has one preferred amplitude that it wants. No linear system has that property. Does that make sense to everybody? So this is one of the things which it seems an awful lot like. It seems an awful lot similar. It's almost the same problem as our little harmonic oscillating Brunt-Weissela air parcel, but it really isn't, because it doesn't, the amplitude is not arbitrary. The amplitude is fixed by the nonlinearity of the governing equation. So one system in the Earth system that you might think of like that is glaciation, deglaciation. You know, as when you glaciate the Earth, you get about 10 degrees cooling over the globe. It's always 10 degrees. It doesn't matter whether the orbital forcing is, you know, one particular alignment of Milankovitch forcing gives you a 1 degree ice age. No, we don't get 1 degree ice ages. We get a 10 or we get 0. And so that is another nonlinear oscillating system. The nonlinearity is in the ice sheets, the albedo feedbacks, the nonlinear is in the sea ice. All of that stuff combines to make the Earth a nonlinear oscillator. The forcing is periodic, but the response has fixed amplitude that it likes to go to. You either are in an ice age or you're not. You can only be transient in between. Does that make sense? So this is a characteristic of many nonlinear systems that they would have a preferred amplitude even when they're oscillating. So the oscillator system that we thought about, the little wave, internal wave, Brunt-Weissel oscillation, and all of the masses on springs and all that stuff that you saw in first year physics and high school physics, none of those are this. But lots and lots of geophysical oscillations are this. Every earthquake that has stress thinning has a preferred oscillation amplitude based on the rheology, the nonlinear rheology of the soils. Every positive feedback system in the climate system with a nonlinear negative feedback has a preferred amplitude that it's going to find in an oscillation above that point. Okay? So in some sense, this is the more natural system, is a nonlinear oscillator rather than a linear oscillator, even though the linear oscillator is one of our favorites that pops out of the Taylor series all the time. These things also pop out of lots and lots of systems all the time. And the Taylor series, where do you do the Taylor series for this? There isn't a fixed point to Taylor series about. We can look at one direction by projecting into the R and theta direction, but we have to like really reconstruct the full phase space to get a sense of it. This single fixed point in the middle is easy to do. We do a Taylor series. Is it spiraling in? Is it spiraling out? We do that whole game. But what do we do for the limit cycle? We just have to find it. Does that make sense? Okay. The last thing I want to say talks about hysteresis, which we have, there are two systems that we talked about with hysteresis. So what is hysteresis? Has anybody read enough to have a sense of what the definition is?
Is it that there's a lag in the, I guess the response to a perturbation, so when you change direction, it behaves differently?
It's not quite a lag, but there's a sense of directionality. So in a linear system, if you're increasing, you go on one path, and if you're decreasing, you go backwards down the same path. There's sort of a reversibility about it. A hysteretical system, one with hysteresis, this is, you start getting tangled up with hysteresis and hysterical and hysterectomy. They all mix in together. Sorry, that's just the weird choice of words. That's what they've done. We're stuck with these funny adjective forms. But anyway, in a hysteretical system, or maybe hysterical system, whatever, depending on how amusing you want it to be, it will go a different path in phase space as it's increasing, as some property is increasing from when that property is decreasing. And the simple way to think about it, we have the Stommel model, and we have the Burico climate system model. Both of them are examples that have hysteresis, and both of them have a bifurcation diagram that looks like this, roughly. So what's our interpretation of a bifurcation diagram? So given a parameter R, this is a steady state solution. So I guess I can put X star. And we then can examine whether it's stable or unstable by following along that. And in the particular case we're interested in, this is a stable solution, and the middle one is an unstable solution. And so these two bifurcation points are where one of the eigenvalues flips sign in the Taylor series bits. Okay? So this might be our ice house Earth, and this is our greenhouse Earth. There's hothouse Earth, and then this in the middle is our state where we might have both states coexisting for the same value of greenhouse gases. Or in the Stalin problem, this is the rate of temperature forcing to salinity forcing, and we might have a meridional overturning circulation that goes one way or the other way, depending. But in both systems, it looks like this. Okay, everybody on board with that? So if I'm sitting over here, happy in my steady state, and then someone starts slowly turning up the heat, changing my greenhouse gases, what's going to happen? I change R slowly enough that I don't break the underlying system. Where am I going to go? My R goes this way, really slowly. So now we're at this point in R. Now where am I going to converge to?
We keep going towards that unstable.
Yeah, I'm going to go along this steady state, or maybe I'll kind of wobble off and then come back, but it's still steady when I stop R at this value. I might go off this way and come back, but as you're marching along in different R's, I'm kind of whatever, coming back. So you turn up the R, turn up the R, turn up the R, moving along. Now what happens if R goes to here? I've just gone whoop, now where do I go? I have to go all the way up to this steady state. So I'll go zoop all the way up to there. Does that make sense? Okay, now what if I reverse the direction of R and start going back towards my original value? What happens? Where do I go? If I go off of this one, I can go boop. I'm going to converge back to my nearby steady state because there's probably, in the phase portrait of, there probably is a separatrix between this steady state and this one. And I'm not going to, if I'm moving gently, I'm not going to cross that. I'm just going to track along with my neighborhood fixed point. Keep going, bloop, 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 bloop. What happens when I get here? I go all the way down there. So, if R is changing periodically in time gently, like Milankovitch forcing, we're down here, ice house, ice house, ice house, ice house, bang. Hot house, hot house, hot house, hot house, bang. Ice house, ice house, ice house, bang. Hot house, hot house, hot house, bang. Yeah.
I don't think I fully understand like the sudden jumps.
When I go off the end here, if R is at this value that's slightly bigger than that bifurcation point, those are no longer solutions that are available to me. The only solution I can converge into is the one all the way up there.
So why can't you go on the dotted line?
Because R is what is controlled. R is the external forcing in this thought process. So R is what, one time R has gone beyond this point, those steady state solutions have just become imaginary. They're no longer there. And so I only have this one. So there is an oscillation that is forced by R that goes on the increasing direction this way, the decreasing direction this way. So if I was to plot this in time, it would look like this. If this was X, then this was time. So it's an oscillation, all right? It repeats. It is definitely not a sine wave. It is definitely not amplitude independent. The amplitude is set by how far apart these steady states are. It's not set by the magnitude of the forcing. In fact, it's kind of, the transitions are set by the timing of when R crosses. But if I bang R all the way out here, it actually doesn't affect the amplitude very much. It just ends up a little bit farther down this steady state. So the magnitude here is set by the distance between the steady states. It's not set by the magnitude of my R perturbations very much. It's kind of a weakly sensitive one. So this is why the Budico model is thought to be a good model of ICHs, is because it jumps back and forth between multiple steady states. And the Stommel model is another one, which is a model of tipping points for the meridional overturning circulation, which may or may not exist in the real world, but in that toy model they definitely do. So these are called tipping points. Here's your tipping point, and you've just crossed the tipping point, and now you no longer have a small correction available to you. You've lost the ability to stay in the state you're in. You have to have a massive, abrupt change. And these are also typical, although that would also be typical of the big boulder with the small support. There's a tipping point. If you push hard enough, the thing falls down. And now if you stop pushing, it doesn't pop itself back up on the state. It's just going to sit on the ground. It also is a hysteresis system. There's a tipping point involved. Does that make sense to everybody? So this is one class of systems. Okay, last thing, which, all right. So can we try and get the projector to work? Let's see. So can you pull up figure 1026 from the notes? Okay, so let me describe while he's pulling it up. So this is a system with two potential wells, just like the one that we had drawn before, except it's not even as complicated. That's just two holes, and so there's a tipping point in between them, and that's the system. So here's the potential, and here's the D. This is the X dot in the X direction. But they add a tweak to it that they put a time-varying forcing underneath. So when I'm very near the tipping point is actually moving underneath me. So sometimes I'm just rocking around this little well, responding to the time-varying forcing, and sometimes I'm up near the tipping point. And sometimes I'm rocking in this well, and sometimes I'm up near the tipping point. And so when you start trying to draw the basin of attraction, you have this funny thing, which is like, if I'm close to this steady state, I'm going to fall into it. If I'm close to this steady state, I'm going to fall into it. And if I'm right on the dividing line between them, I would normally just sit still. That would be an unstable fixed point. But in the presence of the time-dependent forcing, I've got kind of an uncertainty. Am I on the unstable point? Am I to the right of it? Am I to the left of it? It depends on the moment that I arrive up there. Does that make sense to everybody? And so instead, you get these kind of wrapping layers on layers. And this, if you do this over and over again, is showing you this phase space. And look at these weird gaps that are going to one place, and then there are other ones going to other. And it looks like phyllo dough, like rolled into itself over and over again. So this concept of a basin of attraction in simple circumstances is really useful. But when we put time dependence into the forcing, maybe it's not so useful. So can you go down to the next figure? Another way we can get an interesting structure is if we go from two-dimensional to three-dimensional. When we do that, the thing that we're falling onto, the thing that is the object, like our limit cycle, can become a fractal in and of itself. So in 2D, the limit cycles can just be rings, or they can be complicated loops, but they're just a loop. But we go to 3D, and you're like, well, in 3D, our limit cycle could be a Mobius strip, or it could be a really complicated fractal. And maybe the most important one of these is the Lorenz Cycle. So this came out of a weather forecasting set of equations. And so you basically, you loop around one node of this, and then you loop sometimes around that one. But how frequently you switch is actually a chaotic, unpredictable thing. And even weirder, if you start two trajectories right next to each other, after a finite time, one of them will get on the other one, and then one will stay on this one. So in a finite time, things that are infinitesimally far apart become finite distance apart. So normally we're like, well, if you forecast the weather, you got temperatures from all over the world, you're like, well, most systems, if our observations were really, really close to each other, we'd eventually get to the same destination. This tells us that that's not true in nonlinear systems. Even infinitesimally, as close as you want to make it, in a certain amount of time, will pop apart. So weather forecasts are limited by about 2 weeks because of this. In the real system, you cannot make a weather forecast beyond 2 weeks because our initialization is even just a tiny bit inaccurate, but a tiny bit inaccurate actually in a finite amount of time explodes to unpredictable. So this is what people call the butterfly effect, that a butterfly in your favorite, weird part of the world can make a hurricane happen somewhere or something else. It's because of this, like a little tiny perturbation changes the system as a whole in a finite amount of time. So that's another characteristic we have. Can we go down to the next one? So that's just showing you that's what the trajectory looks like. Those are points along the trajectory. We keep going. All right, this is maybe the coolest one of all. So we talked about the basins of attraction of two of those points. This is one where we have 3 attracting locations, and there's a pendulum swinging in between them. So the pendulum is nonlinear because it has, there's like a sine theta in there, essentially. And each of them is magnetic, so if you get on one of those fixed points, you fall into it. There's the red, the green, and the blue. And this is drawing the basin of attraction. So all these green points over here eventually end up over there. But they start off over here and they go woo, 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 and then go over there. And then the one right next to it is red, so it goes woo, 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 and then ends up there. And if you zoom in on this, it looks like that again. And if you zoom in on that, it looks like that again. And if you zoom in on that, it looks like that again. So it is as deep as you want to go. Like, look at this little one. That one looks sort of like, there's a red, green, blue. It's like a distorted version of the big one. And so it's built into that system. If you just try and draw the basins of attraction, there is a fractal there. So things get really crazy when you go nonlinear, and things that seem like they'd be a good idea, I'm just going to draw the basins of attraction of my different fixed points, can be really dangerous when you're in these interesting nonlinear systems. Not all of them are like this. So Ed Lorenz, who came up with the Lorenz Attractor, I saw him give talks about that a few times, and he said, in his whole career, he lived to be like 90, and was publishing until like the day before he died. He never found a method to be sure that the answer was going to be chaotic. So he knew what the necessary ingredients were for chaotic, like had to be third order and higher dimensional, but like give yourself a greater than 3 order dimensional system. Is it chaotic? No way to tell until you check it out. And so the weird ones that happen are really weird, and the ones like, which seems like this is a really simple problem, but it's not actually, it's a really complicated problem, they're all just kind of lingering around. One of the ones, actually I should have said a little bit more, this isn't quite the pendulum problem, this is actually based on the Newton's method, iterative method of which place you go. So you sit there and you do a Newton's method, and you do a Newton's method, and you do a Newton's method. So remember how we said Newton's method is going to be awesome, and you're going to just go down the descent direction to a fixed point wherever you are. When you get into high dimensional spaces, fractals start popping up in your Newton's method for which solution you fall into. There are 3 possible solutions, but the space of initial conditions and which one it goes into is actually a fractal. So nonlinear systems are really, really hard. That's why we keep Taylor seriesing, we keep Fourier transforming, throwing away the complicated bits. We keep doing that because locally in here everything is nice and happy, and we do our Taylor series. We just wrote down the complete solution for what it looks like there. But globally, in a nonlinear system, things can get weird, even though you should try and see if it's weird before you give up on it. So we found lots of nonlinear systems that definitely aren't weird. So nonlinear systems, there are more possibilities than linear ones. Does that make sense, everybody? Okay, cool, we gotta go.